This gave him the idea that there might be natural materials that could be used to combat disease-causing bacterial growth. Unfortunately, lysozyme is not useful for that purpose. But this did prepare his mind for the possibility, which was realized 6 years later in 1928, when he noticed that a mold growing on one of his dishes had also killed the bacteria in the dish. He named the active agent secreted by the mold penicillin, but he was unable to isolate it. He wrote a paper describing his findings that was published and soon forgotten. A decade later at Oxford, Howard Florey and Ernst Chain were investigating lysozyme and its target, the bacterial cell wall. They wanted to learn about the nature of lysozyme and its action upon the target. Florey had similar humble beginnings to Röntgen. He was the son of a shoemaker in Australia. He came to England on a Rhodes Scholarship and rose through the ranks to become director of the Sir William Dunn School of Pathology at Oxford. Ernst Chain was a refugee from Nazi Germany and a musical as well as a scientific genius. And he was Florey's first hire in the school that Florey came to direct at Oxford. The two together, who had a somewhat troubled relationship, both being temperamental in nature, could agree on one point, and that was that they should extend their study of lysozyme to what they believed to be other lysozymes, antibacterial agents coming from a variety of organisms. For example, penicillin. Now, Chain, as it turned out, had a near photographic memory. He could remember everything he read, and when they made this decision, he could recall having seen the paper by Fleming that everyone else had forgotten. So they thought they would investigate penicillin, as I say, believing it to be a lysozyme. Soon, Chain succeeded where Fleming had failed in isolating the material, discovered it was not a protein, it was not lysozyme, it was a small chemical that could serve an important therapeutic purpose. And he and Florey demonstrated its value by studies on mice. But there remained the problem of obtaining sufficient quantities for human use. And this was an enormous challenge, which was eventually surmounted by the collaboration of literally dozens of institutions, universities, government agencies, research foundations, and pharmaceutical companies, all working together in the late 1940s and early 50s to finally realize the potential of penicillin for its therapeutic application. The result, as I have said, was the virtual eradication of bacterial disease, and for this achievement, Fleming, Florey, and Chain shared the 1945 Nobel Prize in Physiology or Medicine. Now, these brief accounts that I have given you of the history of X-rays and antibiotics serve, first of all, I think, to reinforce the crucial role of basic research. They also illuminate this process of discovery. If you can move to the next slide. Work leading to discoveries is invariably done by individuals free to explore and follow the path of science wherever it may lead. All such paths lead ultimately to underlying principles, to fundamental truths of nature. And it is from this knowledge, from deep understanding, that practical benefit ultimately derives. Discovery is the engine of progress. Discovery and its offspring, technology, are all that separate us from our original primitive condition. Discovery is the hope of progress, hope for advancement in the future. Now, the importance of discovery for medical, economic, and even military benefit has not been lost on central planners. The problem is that discoveries, by their nature, can't be planned. They arise, as I have told you, from untargeted research. They arise by what Sheldon Glashow in his remarks referred to as serendipity, beautifully illustrated by the work of Röntgen, by Fleming, and by others. The only way to assure a flow of discoveries that will benefit us all is by the support of talented individuals everywhere, including at this university and elsewhere in the world, in the unfettered pursuit of knowledge. This important lesson of the past, so well established by the experience of the past century, is often forgotten by people in government and in industry, who desire greater, more immediate financial and other gain. I can recall the words from quite some time ago when I was a young person of the American president at the time, Lyndon Johnson, who lamented what he called life-saving discoveries locked up in the laboratory, and he pleaded for more translational research. This serious sentiment was mistaken. Application of existing knowledge is not the limiting factor in solving our problems. The knowledge itself is limited. As an example, it's been remarked that we know about 1% of all of human biology. In fact, the truth is we know less than that tiny fraction of 1%, and I can easily demonstrate that to you in quantitative terms. Point is, that tiny fraction of knowledge of human biology has an enormous benefit to our health, as we've just discussed, to our economies worldwide. Imagine how great would be the benefits of knowing the remaining 99.9%. Another lesson from the past, if you'll change the slide, relates to the support of basic research. This has traditionally come from governments rather than from industry, and for a good reason. The timeline is very long. Fundamental problems, the kinds of discoveries to which I've alluded, take decades. Only the public with a long-range interest in bettering the human condition will support an undertaking on that timescale. Industry with a short-term interest in the bottom line can hardly be expected to do so. What CEO could report to his or her board that a major investment has been made in research that may or may not become profitable in 20 years or longer? Impossible. Now let me give you a concrete, very recent, and I would say even a frightening example. It's a true example. I have it on good authority. Pharmaceutical companies today developing anti-cancer therapies are regularly, on a weekly basis, forced to choose between a drug that will cure cancer with a single dose and a drug that must be administered weekly and prolongs life for only a year or two. Management always makes the right decision on behalf of shareholders and pursues the less effective drug. This is not an isolated example. Again, I am told by the best oncologists in the world this happens on a weekly basis. Government clearly has a special responsibility and a unique role to play. The return on investment by government in basic research has been huge. The eradication of polio, the cure of childhood leukemia, and many other diseases have not only saved vast amounts in treatment and productivity, not to mention human suffering. The investment has been repaid many, many times over. The investment was even very small to begin with. The annual budget for cancer research in the United States today is $5 billion, less than 10% of the annual expenditure on soft drinks. Less than a week, less than 1 week of the cost of the lamentable war in Iraq. Now you, in this audience, others in very many places around the world may ask, why not wait for a large country like the United States with its rich government to fund basic research, publish the new knowledge, and then benefit? Why shouldn't smaller countries like Malaysia or Thailand or many other places that I visited where there are also very fine universities around the world concentrate on applications that have particular economic or, unfortunately, in many cases, military or other value? The answer is the importance of leadership. Those who create new knowledge will lead and most benefit from its application. To me, the most obvious examples are high-tech and biotech, both of which began next door to where I live, next door to the universities in the San Francisco Bay Area, where the discoveries that led to these technologies were made. Others around the world have joined in the rewards to a very great extent, but the leaders have been vastly more economically and otherwise successful. Not only in the past, but I'm afraid also in the future, and that is because not of the discoveries, not of the knowledge, not of the existing technology, but of the people, because of the talent that drives the enterprise. The best and the brightest still come to train in the San Francisco Bay Area, and many of them will remain after attracted, sometimes after having trained elsewhere. It is crucial for other places, other countries, to compete, to retain their native talent, and to recruit from abroad as well. A marketplace for talent is in the best interests of all. A market for the employment of young scientists is of particular importance, not only to retain their talent, but even to encourage them to do science in the first place. The choice of a career in science represents a great sacrifice. A passion for science must be weighed against a long period of training, 10 years of postgraduate study at low wages, and the possibility, I'm afraid, of no career at the end. The importance of young scientists cannot be overstated. Progress in science, and discovery in particular, is the work of young minds. Now, the marketplace for talent, to which I've alluded, is both academic and industrial. And I should say, by emphasizing the crucial role of government in the support of science, I don't mean to diminish the importance of industry. I've already noted the vital contribution made by pharmaceutical companies in the development of penicillin. This is not an isolated or a rare example, but rather an illustration of a time-honored process. Industry has been and will remain primarily responsible for translating discoveries made in academic laboratories into commercially viable technologies. The time scale for industrial development may be small, but the financial scale is certainly not small. A pharmaceutical company will invest hundreds of millions of dollars in the improvement and testing of a single drug to gain regulatory approval. Now, if I may have the next slide. Basic science may be a cure-all for practical problems, but what possible relevance does it have to social issues? Questions of human rights, of international peace, of other things that concern us so much in the world today. On one level, let me simply state the obvious. You can read it in very many lectures written by others, and I won't belabor the point. The practice of science is truly an example of international cooperation. A majority of the young scientists in my own laboratory over the years, a majority have come from Europe and Israel, from Asia, and from Central and South America. And my laboratory is no exception. The findings made by these young people, and indeed by everyone in science, are published in a worldwide scientific literature. It's available for everyone to read, to criticize, and eventually to exploit. Now, to turn beyond that obvious point, it is often remarked, and it is true, that education is important to combat hatred, intolerance, and other afflictions in society, but education in general, and scientific knowledge in particular, is not enough. It turns out not to be the universal prescription for social ills. The most learned society, perhaps in the history of mankind, that of 20th century Germany, perpetrated, as you know, the worst offense against humanity, the Holocaust. More than half of those who planned the mass murder of the Jews at the Wannsee Conference in 1941 held doctoral degrees